Hello, everyone. Okay. I'm Liangyue from Arizona State University. I'll present our paper, QUINT, on query-specific optimal networks. This is joint work with Dr. Yuanyao from Nanjing University, Dr. Jie Tang from Tsinghua University, Dr. Wei Fan from Baidu, and my advisor, Dr. Han Tong. So node proximity measures the closeness. Node proximity measures the closeness or relevance or similarity between two nodes on the network. For example, in a figure, the numbers indicate the proximity score from each node to the query node 4. The more red the node is, it is more closer to the query node. So node proximity can help answer questions like, what is the closest node to node 4? So node proximity is a building block in many application domains. For example, in biology, given a disease similarity network, a generic protein interaction network, a known gene disease associations, node proximity can help infer genes that are associated with a certain disease. In social network, for example, on Facebook friendship network, node proximity can help us find friends that we might know. In e-commerce, node proximity can help recommend products that the user might be interested in buying. And in disaster management, node proximity can help users identify potential contacts for report sharing and community organization. So a popular choice for node proximity is random walk with restart. Its success is mainly due to its flexibility in summarizing multiple weighted relationships between two nodes. So there are many variants of random walk-based approaches. For example, electric networks, Couch algorithms, matrix forest-based algorithms, and all these variants are based on very similar idea. So so random walk with restart works as follows. So a random surfer starts from the query node. At each step, it has two options. Either it can transmit to one of its neighbors with probability proportional to the edge weights, or it can jump back to the query node with a certain probability. So the formulation for computing the proximity score from query node S is as follows. So RS is the ranking vector. It equals C times A, which is the adjacency matrix, times RS, plus 1 minus C times ES, which is the starting vector. So we can compute the ranking scores either using iterative power method, or we can use a closed form solution involves a matrix inverse. But here the assumption is how to best leverage the fixed input graph A. Some recent work tried to optimize the edge weights from site information to learn a beta graph. So the site information include users' feedback, node attributes, or edge attributes. So a key idea behind supervised random walk is to infer an optimal edge weights. So this is their formulation. So they infer the edge weights from the attributes of the edges so that the proximity score from the query node to the positive node is greater than the proximity score from the query node to the negative nodes. Though they try to optimize the edge weights, they assume that the network has a fixed topology. So in this paper, we try to answer the following three algorithmic questions. The first question is, shall we learn an optimal weights, or shall we learn an optimal topology? The second question is, shall we learn one network to fit all the queries, or shall we learn one network to fit one query? And the third question is, shall we do offline learning or shall we do online learning? For the first question, optimal weights or optimal topology. Here our observation is that real network is often noisy and incomplete. So here the challenge is, how can we learn optimal topology as well as optimal weights so that the weights of the noisy edges can be reduced and we can infer those missing edges? The second question, one fits all or one fits one. Here our observation is optimal network for different queries might be different. For example, on the left figure, the query node 1 has 2 positive nodes, 4 and 5, and it has 2 negative nodes, 9 and 11. So in the optimal network for the query node 1, it is more closer to the nodes 4, 5, 6, 7, and is far away from nodes 8, 9, 10, 11, and 12. On the right figure, the query node 3 also has 2 positive nodes, 9 and 11, while it has also 2 negative nodes, 4 and 5. So in the optimal network for query node 3, it is closer to the nodes 8, 9, 10, 11, 12, while far away from nodes 4, 5, 6, 7. So here the challenge is, how shall we tailor the network learning for each query? So the third question, offline learning or online learning. Here our observation is that in supervised random walk, where they try to optimize the edge weights, it involves a costly iterative subroutine to compute a single grading vector. If we want to learn the optimal topology, then the parameter space will expand to n squared. If we want to learn one optimal network for each query, then we could, in principle, we could have n cubed parameters. So here the challenge is how to perform query-specific online learning. To formally define the query-specific optimal network learning, we are given an input network, A, a query node S, positive nodes P that the query node wants to connect with, and negative nodes N that the query node wants to avoid connecting with. So here the task is to learn an optimal network AS that is specific to the query node S. So in this paper, we propose an algorithm called QUINT to solve this problem. And this is our formulation. So first, in the objective, we want to match the input network so that we want the learned network S to be as close as possible to the input network A. And second, in the constraint, we want to match the preferences. That is, we want the proximity score from the query node to the positive nodes to be greater than the proximity score from the query node to the negative nodes. So here the matrix Q stores the pairwise proximity score from node I to node J, and it can be computed in the top right corner. So as a remark, in this formulation, we are searching in the larger parameter space, that is n squared. And we are learning a query-specific optimal network. Notice that in the constraint, there is no exception allowed, which is not often satisfied in practice. But we can use a loss function to relax this constraint and get our softer version. So here, the loss function G is to penalize the violation of preferences. And it satisfies the following conditions. If the proximity score from the query node to the negative node is indeed smaller than the proximity score from the query node to the negative node, then there is no loss. Otherwise, there is a positive penalty. In this paper, we use Wilkinson-Whitney loss. If you are familiar with supervised random walk, then you might notice our formulation bears a high-level resemblance to supervised random walk. So it is indeed not very hard to formulate the query-specific network learning. The difficulty is how to efficiently solve this formulation. And because this formulation is non-convex, so our hope is to find a local minimum. So we use gradient descent-based solution, and this is how we compute the gradient of the objective function with respect to S. And instead of walking you through the details, let me give you some intuition behind this computation. In the illustrative example here, given a query node S, a positive node X, how can we update the link weight Aij? So from the formulation here, the update to Aij is proportional to the proximity score from S to J times the proximity score from I to X. So if I is a close neighbor of X and J is a close neighbor of S, then there is a large increase on the link Aij. So the probability from S to X is also increased. So the overall complexity is as this. So T1 and T2 are iteration numbers. P and N are the size of positive nodes and negative nodes. M is the number of edges. N is the number of nodes in the network. So usually T1 and T2, P and N are much smaller than the network sizes. But the complexity is quadratic to the number of nodes, which is often very large in practice. So the question is, how can we scale up the computation? So we propose a scale-up solution. So the key idea is to assume that the network, the optimal network, is the rank 1 perturbation to the original network. So this is our formulation. So F and G are two column vectors. Then F times G prime will be a rank 1 perturbation. And its formulation is similar to our previous formulation. And we use alternating gradient descent to solve this formulation. And the complexity can be reduced from n squared to n. We also provide two variants to further speed up the computation. The first variant, the key idea is to apply a Taylor approximation for the matrix A. So the complexity using first-order Taylor expansion is big O T1 P times N times N. So here the benefit is we can access QIJ much faster. So in our second variant, the key idea, second variant, which is localized rank 1 perturbation, our key idea is to only update the neighborhood of the query node and the neighborhood of the positive and negative nodes. So the complexity is as follows. So NS is the neighbors of S, and NPN is the neighbors of positive nodes and negative nodes. So usually maximum of the neighborhood size of S and neighborhood size of positive nodes and negative nodes is much smaller than the number of nodes in the network. So here our benefit is that the complexity is usually sublinear to n. So for the experiments, well, we use over 10 diverse real networks from 5 categories, and we use link prediction to validate our proposed algorithms. So the first figure shows the mean average precision results, and the higher is better. These are all the competitors. So our algorithm can perform better than the other competitors across different networks. The second figure shows the HalfLife Utility results. Again, the higher is better. And so we also observe that our proposed algorithm is performing better than other competitors across different networks. And same observation for AUC results, precision at 20 results, and recall at 5 results. And this figure shows the mean percentile ranking results. Here, the lower is better, and our methods still perform better than others across different networks. So this figure shows the scalability plot. It shows the running time versus the number of nodes and number of edges. So we can observe that our QUINT rank 1 version can run in less 1 second on the billion scale network, and it scales sublinearly. In conclusion, in this paper we propose, we try to learn an optimal network for node proximity, and we propose an algorithm called QUINT. It can learn an optimal topology, and it can learn 1 network to fit 1 query, and it can do online learning. So the heart of our algorithm is a very efficient way to compute the gradient of the proximity score with respect to each element of S, with rank 1 approximation, Taylor expansion, and local search. And experimental results shows that our proposed algorithm can consistently perform better than others on 10 networks on 6 metrics. And it scales sublinearly, and it has near real-time response on billion scale networks. That's it. Thank you.
Okay, so we have time for a few questions. So for people who are sitting on the side, you can use a microphone over there. Sitting in the middle, you can use this phone. Okay. So any questions regarding to the presentation? We have no questions? Yes, go ahead. You can use a phone here.
So when you calculate the precision, what was the ground truth for node proximity?
So we actually reserve. We use 50% of the links as training, and then the rest to test our algorithms.
So, sorry, I didn't.
So we randomly select 50% of the links as training, and then the rest as the test.
The ground truth was measured by supervised learning, right?
What's that?
Ground truth was measured by supervised learning. So that's what
no, you know the ground truth from the data. So as I said,
my question is, how do you know?
What's that?
My question is, how do you know the ground truth?
Yeah, as I said, we reserve 50%. So we hide the 50% of the links as tests. So we know which are really linked together.
Okay, so you have more questions? Go ahead.
Okay, so I'm sorry for a stupid question, but I missed what are the representation. What are the representations of nodes? So in fact, if you need to learn something, some adjacency matrix, you need to model it as something depending on features, I guess. Yeah. Features of nodes, edges. Yeah.
So we didn't use the features of nodes and features of edges. We
So
didn't use the attributes of the nodes and edges.
Sorry, you used?
We did not use the attributes of the nodes and the attributes of the edges.
Okay, but in this case, I believe that the optimal agency matrix is, so the optimal network is just to connect the query node to the positive nodes and not to connect to the all the other nodes, isn't it?
No, because there might be some noisy edges in the network, then you need to remove them. And so there might be also connections from the neighborhood of the query node to the neighborhood of the positive nodes. So it doesn't necessarily just directly connect the query node to the positive nodes.
So I think what you suggest is actually one comparator method that we tried. So just to connect the positive node and just to disconnect those negative nodes. That's one of our baseline methods that we tried. So that's to some extent effectiveness, but in our work we show that we can do better than that by also optimize the other links. Yeah.
Okay, thank you.
Thank you.
Okay, thank you. So do we have any other questions? Okay, if no questions, let's thank the speaker.